Hi, and welcome to the second video of my series of what's probably going to end up being 3 videos about the pdp-8e computer. So here we're looking at the front panel. In the previous video we sort of did a tour of the hardware, and in this video I want to write a short program. I'm going to use the front panel to write the program, entering it in binary with the switches on this row here and controlling execution with these switches over here. There's several rows of light bulbs up here that we'll use to look at our output. The top row always contains the memory address that's being referenced in whatever way, and the second row can display one of 6 things selected by this rotary switch. We're going to use the accumulator and the memory data, these 2 positions. And really the only thing I'm going to use the accumulator for is to show you a sort of cool thing that happens when you turn this machine on. So let's turn it on. And you can see that the lights scan back and forth. Anyway, I thought it was slightly cool. So what we're going to do now is enter the same program which I demo in class in Computer Architecture Comp 4300 here at Auburn, and it's a program to add 2 numbers, and we'll store it starting at address 0. The program's 5 instructions long, and it consists of a clear accumulator instruction to put a 0 in the accumulator, 2 2's complement adds to add the 2 numbers, which we'll just use 2 small positive integers as our numbers to add, which we'll store in main memory, and just add those to the accumulator. Then we'll store that back to a different address, and then we'll halt. So those are the 5 instructions, and then we'll use 2 more words of memory to store the data, and yet a 3rd word of memory for the result. So to enter data, I put in the address where I want to start entering data. I'll flip this down to memory load. Those LEDs are nonsense at the moment. And I'll press down the address load switch to show us what's in address 0. And something's in there, just whatever happened to be randomly initialized. This pdp-8e has semiconductor memory, so it doesn't retain the contents of memory from power off to power on the way the core memory would. Okay, so the clear accumulator instruction, which we would just look up from the pdp-8 programmer's reference card, is octal 7200. Each 3 switches represent 1 octal digit, so 7 111 2 010 00 is what we'll enter in, and then I'll flip the deposit switch over here on the far right to put that value in address 0, and then automatically increment the address. So it shows me the value I put in address 0, and it shows me the incremented address. This address incrementing was a problem for this machine for roughly a decade. It took me that long to debug it. One of the bus driver chips on the CPU boards was not correctly amplifying the output of the adders and the one that it should be to increment the address properly, either when you're doing things with the front panel or when you're executing a program normally. In any event, that's fixed and addresses are incrementing normally. Though we could have gotten this far before I fixed it, because the previous address was 0, and that was what was happening. We were always adding 0 to 1 rather than the prior address to 1. Okay, so that's our clear accumulator instruction. 2's complement add, the next instruction, is opcode 1, so 001 in the first 3 bits. And then the next 2 bits control whether we're doing direct or indirect addressing and whether we're on page 0 or the current page. Our code is on page 0, so page 0 is the current page, and we're going to do direct addressing, so we don't need to fool with those 2 bits. We can leave them both 0. And then the last 7 bits are the offset within that page. A page is 128 words of memory. continuously, and page 0 are words 0 through 127. So we're going to put in the offset on page 0 of the first operand we want to load, and that's going to be address 5. Our program will occupy addresses 0, 1, 2, 3, 4, and then we'll put our two operands in addresses 5 and 6. We'll store the result in address 7. So let's put in the offset 5. So 2's complement add of the contents of address 5. Next one will be a 2's complement add of the contents of address 6. And then we'll deposit and clear the accumulator to store our result in memory. That's opcode 3, 0, 0, and we'll put it in address 7. So now we're up, the next instruction will be the halt, the last instruction of the program. There are a number of opcodes that will halt the computer, but 7402 works. So let's put that in at address 5. Now we're done with our program. We'll put in our two operands at address 6 and 7. And let's add octal 24 and 34 so we can see at least a little carrying going on. 0, 0, 2, 4. So that's 2 times 8 plus 4, or 20. In decimal is the first operand we're storing. For our second operand, let's use 34. So 3 times 8 is 24 plus 4 is 28. And 24 plus 34, doing the octal arithmetic, 4 plus 4 is 8, so 0 carry the 1. 2 plus 3 is 5, plus the carried 1 is 6. 6, 0 ought to be our result that we'll see in address 7, which is octal 6 times 8, or 48 in decimal. So in address 7, we need to put something other than octal 60 to make sure that it actually changed. Let's put in octal 77. So let's look at everything now and make sure that it's there. So I'm going to go back to address 0 and start looking at things. 7200, that's our clear accumulator. 1005, 2's complement add the contents of address 5. 2's complement add the contents of address 6. Depositing clear accumulator to address 7. Halt. 24 is the first operand in address 5. 34 in address 6. And 77 in address 7, which we'll hope will be overwritten with a 60 when we run the program. So now we'll go back to address 0 to run the program. Make sure that that halt and single step are both up. That is, we're going to run normally, and hit continue. The program ran, and this is a little bit encouraging in that the address that it shows is address 5, which would be the next instruction after the halt. So it looks like the program ran the correct number of instructions at least. So let's go look at what's in address 7. So we'll put a 7 there, address load, and examine. Excuse me, and indeed we find 6, 0 instead of 7, 7. That's what we wanted. So looks like the program ran correctly, and that concludes this video. In the next video, hopefully, I will hook up a terminal, load some paper tape, or at least simulated paper tape using the terminal to simulate the Teletype Model 33 paper tape reader, and we'll run some big boy programs like a programming language or debugger or something. So I will see you in the next video.